I'm Rosemary Halenza.
I am Victor Gomez Ruiz.
I'm Ryan Schroeder.
I'm Spencer Morshing.
I'm Bennett Eisenbeiss. Our team was tasked with integrating this octocopter drone with a robotic manipulator. Our goal was to be able to pick up and carry a full 12-ounce pop can. Similar projects have been completed before, but nothing with this reach and payload have ever been done. Our manipulator has 5 degrees of freedom, 60 centimeters reach from the center of the drone, and a max payload of 400 grams. The greatest challenge of this project was our budget of only $200.
The first thing we had to do with this project was to ensure that the current design would work for our objective of picking up the soda can. By weighing the parts and motors, we were able to set up statics equations to illustrate the required torques for each joint.
Once we knew the required torques, we had to see if the servos we inherited were able to hit these values. An apparatus was set up with a servo spline attached to a 10 centimeter long bar. At the end of this bar, we were able to hang weights to create a moment around the center hub of the servo. After doing this testing, we found that only 2 servos hit the required torques. At this time, we knew changes had to be made to the design in order to utilize the maximum number of the servos we inherited from the previous project.
Our calculations proved that an arm with equal lengths required torque values that could be obtained using the current servo motors and a single new higher torque motor. By testing the servo motors to obtain their actual operating torques, they were rearranged to satisfy all theoretical torques required at each joint.
The effector was redesigned to reduce weight and simplify the mechanism for grabbing the soda can. The redesigned effector reduced the overall weight by 70 grams while allowing for a larger range of motion. A small servo was chosen for opening the effector, and 2 springs were mounted on the effector for the closing motion. Using these springs, we were able to turn the power off to the servo and still firmly hold the can.
The lateral swivel mount was redesigned to improve the previous design, which had an excessive amount of play. The improved design allowed for the arm to have more accuracy in picking the target load up. A simple design of 2 aluminum plates were used to act as the bearing. Teflon sleeve bearings were placed in the slotted channels to reduce friction. Additionally, lithium grease was used on the bearing surfaces to further reduce the amount of friction while maintaining a tight bearing design.
A program written with the processing environment was used to establish communication between the computer and the Arduino controlling the arm. This communication can be established via USB or with an Arduino Bluetooth module, such as the HC06. A user-friendly interface was created to facilitate the usage of the arm.
The operator will control the manipulator with their computer, which can communicate via Bluetooth with an Arduino Uno on board the drone. The challenge with controlling the arm is calculating where each of these joints needs to move to when we tell it to go to a certain position. To accomplish that, we implemented an Arduino library, Fabric 2D, which uses a method called forward and backward inverse kinematics to calculate where each of these joints needs to go with very few iterations. Unfortunately, due to some electrical noise that we weren't able to solve before lockdown prevented us from working in our lab, we aren't able to show you the arm operating today.
High-frequency electronic noise coming from the network and from the connection wires causes jittering in the arm. A silent key low-pass filter with the cutoff frequency at 60 Hz is recommended to implement to avoid that jittering. DC-DC step-down converters were used to adapt the 14.8 volts from the batteries to the 5, 7.4, and 8 volts required by the different servos of the arm. For each set of equal input voltage servos, a Pololu Micro Maestro driver was used to supply the power from the batteries and the controls from the Arduino.
The drone had gone untouched for about a year after suffering a minor crash during the final stages of the first team's project. So the first step was recovering lost components. Once the drone was fitted with the proper components, tethered flight testing began. Early test flights were promising, but with campus closure we were not able to resume flight testing. The remaining work on the drone was done with simulation. The drone was modeled in Simulink by adapting a provided quadcopter model. The gains were tuned until the drone could successfully take off and follow roll, pitch, and yaw commands. Once the manipulator and drone systems were functioning separately, the full system was modeled by accounting for the mass of the manipulator and shifting the center of mass as it would for the manipulator moving to target positions. The simulation of the system was promising, showing minor overshoot with quick settling time even in the most extreme cases. Despite the difficulties, we are able to make major improvements to the system. The manipulator is now capable of holding its own weight plus a load. The effector was redesigned to reduce weight and grasp a wider range of objects. The mount was redesigned to increase stability. Manipulator control code was created. The drone was returned to working order, and the simulations were completed to show the viability of system integration. We hope to leave this project in such a way that a future team can pick up where we left off by completing flight testing and refining the controls.